Welcome back. In our last session, we took a look at electric fields and how they relate to potential and capacitance. In this session, we'll follow it up with a look at Gauss's law and how to use it to calculate the capacitance of different configurations. Be forewarned, I will be getting down and dirty with some math, but before we get started, let's have a word about that. Math tends to get a bad rap, and I don't think that's fair. As an engineer, I see math as an essential tool of the trade. A bit like a good wrench for a plumber. And it's all about using the right tool for the job. I firmly believe that you have to have a working model in your mind when you are taking measurements of real-world circuits, and especially when you have to go off script and start troubleshooting them. You probably use working models every day without realizing it. I'll give you a simple example. Let's say that tomorrow you plan to drive to an appointment in a town that is 40 miles away, and you need to decide when to leave to get there on time. Do you just pick a time randomly, or do you use some working model and a set of assumptions to make a more informed decision? If you can take an expressway the entire way and travel at a constant speed of 60 miles per hour, or 1 mile per minute, then you can get there in 40 minutes. But this should be treated as your bare minimum. You'll likely need to add some time on either end to get to and from the expressway, and you'll need to account for traffic depending on the time of day. But all in all, you should expect this trip to take on the order of an hour, give or take. Clearly, you are not looking for a precise time down to the second or microsecond. You are simply looking for a ballpark estimate that you should allow about an hour for the drive, as opposed to something on the order of 10 minutes or 10 hours. If your thought process was anything like this, then you used a working model and some math to arrive at your estimate. These analytical techniques I am about to show you are all about doing essentially the same thing. An understanding of these analytical techniques and the physics behind them can prove invaluable in helping you diagnose a problem much more quickly and efficiently than just using a hunt and peck approach. Many years of experience talking here. So with that, let's get on with it, starting with Gauss's law. At its most basic level, Gauss's law says that an enclosed charge produces an electric field. More specifically, it states that the total outward electric flux through a closed surface is equal to the net charge enclosed within it. Some textbooks use a term called the electric flux density vector D, which is the electric flux per unit area and is defined as the permittivity multiplied by the electric field. I don't generally use D, I just go with epsilon E because I know right away what that means, but I want you to be aware of it should you ever come across it. The units of flux density provide some additional insight, as is usually the case. Permittivity is expressed as capacitance per unit length in units of farads per meter, and electric field is in units of volts per meter. Remember that capacitance is defined as charge divided by potential, which can be rewritten as Q equals CV. Thus, a farad volt equals a coulomb, the unit of charge, and the units of electric flux density are coulombs per square meter, or charge per unit area. The total electric flux is the integral of the flux density through the closed surface enclosing the charge. Moving epsilon to the other side gives the more familiar form of Gauss's law, which states that the integral of the electric field through a closed surface is equal to the enclosed charge divided by the permittivity. As we'll see, Gauss's law is a useful tool for calculating capacitance of different configurations. We can use the geometry of a given shape to define the closed surface to simplify the integral as much as possible. For a small spherical charge, we can define our surface to be a larger sphere of radius r with the charge at the center, and the integral simplifies to the electric field magnitude at the distance r multiplied by the surface area of the sphere, 4 pi r squared. We then solve for E to get the enclosed charge divided by 4 pi epsilon r squared. And you may well be saying, now I can calculate the electric field from a point source. How nice. Well, yes, that's mainly a simple theoretical construct to illustrate the basic concept. But hang on, there's more. Going back to our definition of electric field as the force applied to an external charge, we can rewrite it to show that the force equals the electric field multiplied by the external charge. Taking the expression we just derived for the electric field from a point source, we multiply by the external charge to get the product of the charges divided by 4 pi epsilon r squared, thus arriving at Coulomb's law for the force between point charges, which was discovered experimentally by Coulomb about 50 years before Gauss published his more general law in 1835. Gauss's law is also sometimes shown in its differential form, stating that the divergence of the electric field equals the enclosed volume charge density divided by the permittivity of the material. In general, I prefer the integral form because it provides a more intuitive description. It gets a bit more interesting and useful when we look at a long uniformly charged cylinder of length L. You might say it looks just a little bit like a wire. Now we define our surface to be a larger cylinder of radius r with the charged wire in the center, and our surface has an area of 2 pi rl. You might say it's starting to look just a tiny bit like a coaxial cable. The total charge divided by the length can be expressed as the charge per unit length, Q sub L. Solving for E gives the charge per unit length divided by 2 pi epsilon r. Recall that the potential difference between 2 points equals the negative of the line integral of the electric field between them. Our inner cylinder has radius A, and our outer cylinder has radius B. These will be our limits of integration, but we need to take a moment to make sure we set this up correctly. We are interested in the potential of the inner cylinder with respect to the outer cylinder, which we will define as our reference. Thus, the lower limit of integration is B for our outer cylinder, and we integrate toward the inner cylinder, and our upper limit is A. Once we have the integral set up correctly, we can cancel out the negative sign out front and reverse the integration limits and carry on from there. But in order to get the correct polarity for our final result, we need to make sure we set up the integral to go from the reference surface toward the surface with the potential of interest. In this example, we have only one charged conductor, and we're really only interested in magnitude. But in the next example, we'll have to pay closer attention to signs and polarity. Now we evaluate the integral to get a potential equal to the charge density divided by 2 pi epsilon times the natural log of B over A. Now, remember that capacitance equals charge divided by potential. So the capacitance per unit length of our concentric cylinders equals the charge density divided by the potential, or 2 pi epsilon divided by the natural log of B over A. And lo and behold, this is precisely the equation for capacitance per unit length for a coaxial cable, where A is the radius of the center conductor and B is the inner radius of the outer shield. This is an extremely useful expression that we'll be using a lot, and it all comes from Gauss's law. Here is a graph of that expression using a dielectric constant of 2, typical for Teflon. Coaxial cables will have a B over A ratio of just a little bit over 1 to maybe 2 or 3, giving a capacitance generally in the range of a few hundred picofarads per meter. Due to the logarithmic relationship, once the B over A ratio is above about 4 or 5, the capacitance does not change much. Another configuration that we will see a lot is a pair of parallel wires. These can form an intentional two-wire transmission line, or they can be two conductors from different circuits, as in our capacitive coupling demonstration. The derivation of the capacitance per unit length for parallel wires is a bit tricky, making creative use of the method of images, some calculus, and a healthy dose of geometry and algebra, which for me, the resident mathicist, is just another tiptoe through the tulips. Looking at the cross-section, we'll set the radius of both wires to A and the distance between the centers to be capital D. The outer surfaces of the wires are equipotential surfaces, and we can think of them as being generated by a pair of line charges, their images. When the wires are far apart, these images are located at the geometric center of each wire. But when the wires are brought close together, which is what we are generally more interested in, the images move off center by a distance d sub I. The distance from the geometric center of either wire to the image of the other wire we'll call small d, which is simply large D minus d sub I. Focusing on the positively charged wire first, we can follow a similar approach as the previous example. The electric field E1 at a distance R1 has the same form as before. To get the potential V1, we integrate from D to A with the image of the negatively charged wire as our reference, and we end up with a similar expression as we did for the coaxial cable. But we have a second conductor in the mix. When we look at the negatively charged conductor, symmetry tells us that the magnitudes will be the same, but we have to pay close attention to the signs. The electric field E2 will have the same form, but the sign is negative due to the negative charge. Physically, this means that E2 points toward the negative wire, but the convention is that the positive direction of R2 points away from the wire. Now we set up our integral, outward to inward as before, with limits of d to a. We can cancel the negative sign in front and reverse the limits, but we still have the negative charge. We take the integral and get the same magnitude, but the opposite sign, as we did for the positive wire. Let's pause for a moment to make sure we interpret the negative sign correctly. For the negative wire, we defined the image of the positive wire as our reference, and the positive sense of V2 to be toward the negatively charged wire. Thus, a negative value for V2 means that the negatively charged wire is at a lower potential than the positive wire, which we expect. But mathematically, we must treat V2 as a positive quantity with the sense shown. The total potential difference between the wires is given by V1 minus V2, and because V2 is negative, the negative signs cancel. This means that the magnitudes add, and the capacitance per unit length is given by the charge density per unit length divided by the potential, or pi epsilon divided by the natural log of d over a. But what of little d? We'd like to get this back in terms of large d, the center-to-center spacing between the wires. Remember that the outer surfaces of the wires are equipotential surfaces. If we take any point M on the surface, the ratio of the distances to the two images must be constant. The two triangles formed by points OPM and OMPI must be similar, which means that the ratios of the corresponding sides must be constant. D sub I then equals a squared over little d, but recall that little d also equals large D minus d sub I, or large D minus a squared over d. Rearranging terms gives us something ripe and ready to plug into the quadratic formula, giving us this expression. Remember that the argument of our logarithm is little d over a, which gives this expression, finally giving us our capacitance per unit length for parallel wires of pi times epsilon divided by the natural log of large D over 2a plus the square root of large D over 2a squared minus 1. Now, for you fellow mathicists out there, note that the denominator is sometimes shown as the inverse hyperbolic cosine of large D over 2a. But hyperbolic trigonometry functions are a little much even for this mathicist. I stick with the natural log because here again, I know exactly what that means and what to do with it. Here is a graph of this expression for different dielectric constants ranging from 1 to 3. In our capacitive coupling demonstration, the wires had a radius of about 0.5 millimeter, and the separation was a few millimeters, giving a d over 2a of about 3. The coupling was partly through air, with a dielectric constant of 1, shown by the dark blue curve, and partly through the Teflon insulation, with a constant of about 2, shown by the green curve. Thus, to first order, I'd estimate the capacitance to be somewhere between these two curves, which is right around 20 picofarads per meter. Our wire samples were 1 meter long, so the total estimated capacitance was 20 picofarads. So now you know where that number came from for the estimated capacitance between the wires. Intentional two-wire transmission lines will generally have D over 2A ratios from just a little bit over 1 to about 2 or 3, depending on the thickness of the wire insulation, and the typical capacitance is in the range of tens of picofarads per meter to about 100 picofarads per meter. When D is much greater than A, the logarithm argument simplifies to D over A. You will sometimes see only this simplified expression, but you really need to know the full expression for wires that are close together, because that's where much of our interest lies. Now we can look at a wire with radius A at a height h above a ground plane, which is the configuration we used in our demonstration. Here we can make use of the method of images. The electric field lines will appear as though there is a negative image of the wire at the same distance on the other side of the ground plane. Now it looks like the two-wire configuration that we just analyzed, and we just have to look at a couple of key differences. Instead of using D as the distance between wires, now we are using h as the physical height of the single wire above the ground plane, so we will substitute 2h for D in our equation for the capacitance per unit length of parallel wires. We can think of the capacitance between the wire and its image as two capacitors in series that are virtually connected at the ground plane. Thus, the capacitance for the wire above the ground plane is twice the capacitance that we would get between a pair of real wires separated by a distance 2h, giving us the capacitance per unit length of 2 pi epsilon divided by the natural log of h over a plus the square root of h over a squared minus 1. Here's a graph of that expression for a dielectric constant of 1, because most of the time it will just be air between the wire or cable and the ground plane. As expected, it looks a lot like the graph for parallel wires, but with twice the magnitude. When h over a is more than about 10, the logarithm argument simplifies to 2h over a, and due to the logarithmic relationship, the capacitance does not change much and is typically on the order of about 10 picofarads per meter. This is a good ballpark estimate to use for wires or cables that are some distance from a ground plane or structure. In this session, we showed what a powerful analytical tool we have in Gauss's law for calculating the capacitance between two conductors. We can use it to set up a surface integral to solve for the electric field as a function of distance r and the enclosed charge. We then integrate the electric field over a contour between the conductors to determine the potential difference, which is still a function of the charge. Then we divide the charge by the potential to get the capacitance between the conductors, as we just did for 3 configurations: coaxial cables, parallel wires, and a wire above a ground plane. Of course, the general principles also apply to traces on printed circuit boards. While the configurations we analyzed in this session can be used to give rough ballpark estimates for capacitances on a PC board, those geometries are much more complex to analyze in detail and are best handled with board layout software. So there you are. Electric fields are not so scary once you relate them to the familiar concepts of potential and capacitance. Next time, we'll talk about magnetic fields and how they relate to the familiar concepts of current and inductance. Ciao for now.